This video discusses dispersion, or the spread of scores in a distribution. Many naturally occurring measurements approximate a normal curve. If you draw a sample of people who take the SAT test, their scores show a range from the lowest to the highest. The greatest number occur in the middle. The normal curve is defined as having a mean represented by 0, and the other measurements are above or below that middle in a bell-shaped distribution where the most extreme measurements occur in the tails. The amount of deviation from that middle position can be averaged into a standard deviation, and each full deviation is measured in even units, plus or minus 1, 2, 3. These are called z-scores, and you can ask SPSS to convert your raw measurements into z-scores. Unlike the mean of a sample, the standard deviation of a sample is not an unbiased estimator of the population. The ways the measurements spread out can vary greatly depending on how normal the sample is. Plus or minus 1 standard deviation in a normal curve includes 68% of all cases, and plus or minus 2 includes 95%. Another standard deviation accounts for over 99%, nearly all measurements. The empirical rule is why the curve is typically normal, and this is the basis for standard scores, similar to z-scores. Designed as a standard score, the mean SAT math score is 500, and the standard deviation is 100. With such information, you can imagine many test takers, 68%, receive between a 400 and a 600, and that most of them, 95%, get a score between 300 and 700. After all, there's a large number of people who take the exam for college admission. Dividing the 68% into equal parts, 34, in the first range of scores above and below the middle point, 50th percentile, the score of 600 represents the 84th percentile, that is 50 plus 34. Dividing the 95% into equal parts, 47.5, above and below the middle, tells us that an SAT math score of 700 is above the 97th percentile, which is why getting a 700 puts the overachieving few into the territory of merit-based scholarship money. Going from 95% to 99 gets us to the range of scores from 200 to 800. As you know, an 800 is a perfect score, and a 200 is the lowest possible score. But not all distributions are normal. If you were measuring the SAT scores of students attending an academic magnet high school, then the range of scores would be more narrow with a higher mean and a lower standard deviation, which is not at all typical of a distribution of all students taking the SAT. The mean math score might be 650 and the standard deviation only 50, meaning nearly everyone fell into the 500 to 800 range. Instead of only 3 or 4% reaching the scholarship money at a 700 score, about 16%, that is percentile 100 minus percentile 84, would score above the plus 1 standard deviation. So far, we've only looked at symmetric distributions. A skinny distribution is leptokurtic, and a flattened distribution is platykurtic, based on a normal kurtosis in the normal curve, not too flattened and not too peaked. The more likely case at the academic magnet high school is a skewed distribution where most of the scores are high and fewer low scores occur on the tail. When the tail points left, it's a negative skew. If it points right, it's a positive skew. SPSS will compute your mean, range, and standard deviation for purposes of describing the distribution. For example, knowing the mean age is 40, but the standard deviation is only 2 years, then you expect that the sample represents young adults, perhaps members of the PTA at a neighborhood elementary school. If the standard deviation for age is wider, the curve looks more normal. But if the mean seems too high or too low, then you instinctively expect a sample distribution that represents a different population than simply all people. It could be all minors or all seniors. But the mean and standard deviation do not reveal skew and kurtosis. For that, SPSS will display the distribution as a histogram. Choose the menu Analyze, choose Descriptive Statistics, and then Explore. We're going to use variable fear of speaking for the 39th student for this example. Click on Plots, then add histogram and normality plots. Click Continue and OK to get your output. To examine skewness and kurtosis for normality, you need to take the statistic for each of those and divide by the standard error to create a z-score. If the z-score is within the range of negative 1.96 all the way to positive 1.96, then the curve is normal enough for that particular test. Another test is the Shapiro-Wilk test, which assumes normality as the null hypothesis. If the value of p, which in SPSS is labeled significance, is less than 0.05, which in this case it is not, you would have had to assume that the distribution was not normal. Another test is to look at the histogram. Visually, this histogram of values for this variable approximates what we expect to see as a normal curve. A visual example makes it easy to see, but there are other tests to look at. The stem and leaf plot takes the different values and displays them. If there is an extreme value, it will be labeled extreme and you can consider it later. In this case, there are no values labeled extreme. There is the QQ plot. The QQ plot contrasts the quintiles of the distribution against a normal distribution. If the values are close to the line, then you need no transformations. Ignore the detrended plot. Finally, the box plot should show somewhat equal-sized rectangles. These are noticeably different, but not extremely so. For this course, we do not obsess about normal distributions, except to note that most statistical tests, the parametric tests, assume normal distributions. There are ways to transform your data into distributions that appear normal if your histogram, QQ plot, or other test values raise your concerns. Here's a link to an excellent video on an easy way to normalize your skewed or kurtotic distributions using SPSS. It's brief and it's a pleasant escape from my voice. See you next time.